Okay, hello. We are talking about limits to population growth. By the end of this lesson, I want you to be able to describe the effect a limiting factor can have on a population, as well as describe the different types of limiting factors. So, we're going to go through those. First, talking about what specifically is a limiting factor. So, a limiting factor is just any factor that controls the growth of a population. So, our population size, we have a mini concept map here. You don't necessarily have to put the concept map in your notes, you can just list these out, or you can have this fun graphic organizer. Whatever works for you. So, population size can be limited by things like competition, predation, parasitism, disease, unusual weather patterns, or natural disasters. And there's a bunch more that can kind of fit into those categories as well. These things, acting separately or together, um, can determine the carrying capacity of an environment for a specific species. So, a limiting factor controls population size by kind of creating that carrying capacity. Then we're going to start off with the density dependent limiting factors. Density dependent factors affect populations really strongly when the population density reaches a certain level. So, the limiting factor is dependent on the density. The more organisms in a population, the more tighter packed together, the more effect that these limiting factors will have. Small scattered populations don't necessarily get hit as hard by these density dependent limiting factors as really crowded ones do. So, some examples of density dependent limiting factors are things like competition, predation, herbivory, parasitism, disease, and stress from overcrowding. And we're going to go through and kind of talk a little bit about each one of these. So, starting with competition, relatively simple one. When populations get crowded, individuals have to compete for resources. So, the more organisms you have in a population, the more individuals you have in a population, the more they have to compete for resources. The more that organisms live in an area, the sooner they use up the resources that are available. And like I said, resources doesn't always mean food and water. It can mean food and water, but it could also mean things like space or even like mating grounds, territory, mates themselves. All of those things can be considered resources that individuals will have to compete for. So, the more organisms that are in an area, the more likely they will have to compete for a resource, and more likely that competition will lead to some of those animals or individuals not surviving long enough to reproduce. Predation and herbivory are also two really important density dependent limiting factors. In a predator-prey relationship, populations of predators and prey can cycle up and down over time. So, for example, if we're looking at a wolf population and a hare population or a bunny population, if the wolf population goes up, they have to eat more, so the hare population will go down. And if the hare population goes down, the wolf population can't get enough food, so some will have to, sorry, that was my dryer. Some will starve off. And now that there's less wolves around, the rabbits will be able to increase more, and then there will be higher rabbit population. And if there's a higher rabbit population, it can support more wolves. And then the wolf population will go up, and then it'll just keep cycling over and over and over again. When we talk about herbivory as a limiting factor, a lot of the times we will talk about it in kind of the same concept as predation. Because if you think about it, um, plants would see herbivores as predators. So we'll have the same kind of cycle thing going where if a deer eats only one type of grass and then that grass population goes really far down, then the deer will starve off and then the grass will grow higher and then we can support more deer and so on and so forth. So it has a similar kind of pattern. We're going to look at that pattern right here. So if we've got our hares in red and our lynx or our wolves, either way, or wolves are a different species. This is just a very similar example. We've got our lynx right here. They are blue. So right here we can see a sudden increase in hare population when the lynx population is going down. So as the lynx population goes down, the hare population goes up. And when that hare population is really, really high, the the lynx population will get really, really high, and then the hares will crash. So, and then if there's no wolves, that hare population will skyrocket, and then so will the lynx population. And as the lynx population hits its high point, the hare population is going to crash. And you can see kind of how these are offset through here. It's not a perfect cycle because there are other factors involved here. But most of the time, if you see that the lynx population is kind of pushed this way compared to the hare population. So we've got hare population goes up, and then because the hare population goes up, the lynx population goes up, and when the lynx population hits its peak, the hares plummet, and over and over and over again. So this is in thousands of animals over years and years and years. So this cycle doesn't necessarily happen. It doesn't necessarily happen from year to year, or from like within a year, like month to month, week to week, day to day. But it can happen over decades, as you can see in this chart. Another example of a density dependent limiting factor is parasitism or and disease. So parasites and disease causing organisms can like we learned, feed at the expense of their hosts. If a parasite or a disease is introduced into a population, if that population's really tight together or really packed into a small area, the disease will spread faster because we've got more contact. This is why we social distance, because and also why we see bigger COVID outbreaks in bigger cities than smaller cities, because the disease can't spread as quickly if we are spread out. So mosquitoes are an example of a parasite. If there is a population or if there will be more mosquitoes in an area where they can get more food than if there were an area where they can't get food. And we talked about our tomato worms a lot, so I figured I would throw in a little parasite infested tomato worm for us right there. So if you density dependent limiting factors depend on the density, meaning that the more organisms there are, the bigger the effect the factor will have on density or on population growth. Sorry. So if a population is really, really pushed together or really, really big, the parasite or the disease will have a larger effect on the population. So that wraps up density dependent. Now we're going to talk about density independent limiting factors. Density independent limiting factors affect all populations in really similar ways, regardless of population density. So these are independent of density. They will hit small populations just as much as they will hit big populations. Are things like unusual weather patterns, like hurricanes or droughts or floods, and natural disasters like wildfires, and stuff like that will act as density independent limiting factors. So we got a drought and a wildfire. Essentially, if a drought dries up a lake, if that lake had a really big population of one type of fish and a really small population of another type of fish, if the lake dries out and there's no water left, both of those populations will be completely wiped out. It doesn't matter if one was bigger than the other. It'll affect them both the same way, and that same way in that case would just be total extinction in that area. Same with wildfires. It doesn't matter if there's a high population or a low population. If you get stuck in a wildfire, that population is going to get hit regardless. So those are density independent limiting factors. They're relatively shorter than the density dependent factors, but they are still very important and can still have insane effects on populations. We're also going to talk about controlling introduced species. So when we talk about invasive species, invasive species are typically species that are introduced to a new environment where they don't have any limiting factors. They don't have natural predators. They will just keep going and going and going because there's nothing to stop them. They have all the nutrients they need. They have all the sunlight they need. They are in exponential growth because they don't have anything to limit their growth in their new environments. And this can cause dramatic effects on existing populations because if an existing population gets all of its nutrients taken by this invasive species or gets all of its space taken by this invasive species, it is at risk for going extinct. So scientists will use artificial density dependent control measures to stop invasive species from taking over. So things like kudzu and zebra mussels, which we'll probably talk about later, are considered invasive species, meaning they are just in a period of exponential growth because they don't have any natural predators or natural limiting factors. So scientists will go through and they will either they'll spray specific pesticides or they'll specifically target and pull out the new species, or they will sometimes they will introduce predators to control a species. Right here, you see a forestry team going through a field and spraying pesticides over invasive species plants. I actually have a friend who does this for a living. Every summer, I always get a bunch of Snapchats from her with that giant backpack of pesticide, just lugging it around the woods, spraying and hunting for invasive species. So this is really, really relevant, and something that happens a lot all over the state, all over the country. So that is how we can use density dependent and density independent factors to control species that otherwise would be out of control. That is the lesson for the day. Nothing too crazy. Your next step is to just fill out the exit ticket that is on Canvas. So if you can go and knock that out for me, please. It's 5 questions. Shouldn't take you too long. Make sure that if you have any questions, you let me know, and have a wonderful day.